up guys, it's Gavin here. Today we are going to talk about finding the surface area of regular polyhedrons without knowing their formula. So basically, we are going to derive their formula, their surface area formula, I mean. And yeah, here's our approach. All the polyhedrons have a certain number of faces that are equivalent in area. Also, all the edges of the regular polyhedrons are equivalent in length. So, since all the faces are equal, we could assume that the surface area of the polyhedron is the number of faces times the area of each face. And that's our approach of deriving the surface area formula of the regular polyhedron. Guys, it's the number of faces times the area of each face. Let's try it out. The first regular polyhedron we are going to look at is a regular tetrahedron. It has the least number of faces as a regular polyhedron, and the name comes from the Greek word desera, meaning 4. So yeah, it has 4 faces. Oh, but now we have the number of faces as 4. Yeah, and now we need to find the area of each face. Let's go. In a tetrahedron, the faces are triangles, so we need to find the area of each triangle. And as we know, the area formula for the triangle is base times height over 2. And in our case, the base is the side of the tetrahedron, so we've got, and we name it x, so we've got x times h over 2. So we've got the number of faces and the area of each face, and simplify we get 2xh. Wait, what if h goes on vacation and we only know x? Let's work it out. Guys, what happens if one of your teacher is absent? A substitute teacher comes. So here, exactly, we are going to substitute h with x. All sides of the tetrahedron are equal, so we get x here as well. This is a right angle because look, 30, 60, 90, 180 in a triangle. So since it's a right angle triangle, we could use the Pythagoras theory. So x, we could state that x squared minus x over 2 squared equals h squared, here, h. And open the bracket, we get x squared over 4. And this subtraction, get rid of the square, we get this. So h equals square root times x, square root of 3 times x over 2. So now we relate this to the formula, to the equation we got earlier, 2hx, which is the surface area of tetrahedron, and we substitute h with this. So 2 times square root times x over 2 times x, and we get x squared, square root of 3 times x squared. Yeah, that's it. Square root of 3 times x squared is the surface area formula of a regular tetrahedron. Alright guys, so we've got a regular octahedron. It has 8 faces and each face is a triangle. So 8 as the number of faces times the area of each triangle, and that's the formula, yeah. The same thing as we did for the tetrahedron, we need to substitute h. So we've only got one variable, x, the length of the edge. And that would be better, yeah. And remember this thing we did earlier? Yeah, that gives us h as square root of 3 times x over 2. We put it in the equation, we get square root of 3 times x over 2 times x over 2. It simplifies to square root of 3 times x squared over 4. And that's an area of an equilateral triangle. It's useful to know this because many regular polyhedrons have triangles as their faces. So if we got a regular polyhedron and it has triangles as its faces, we can actually just use the number of faces of that specific regular polyhedron times the triangle formula. Yeah, because it has triangles as its faces. So the number of faces of the specific regular polyhedron times the formula. That's it. In our case, we've got an octahedron. So 8 faces times this, the area of the area of triangle, square root of 3 times x squared over 4, and we get 2 times square root of 3 times x squared, and that is a surface area formula for the octahedron. Guys, I just realized I was calling this tetrahedron, but it actually is called tetrahedron, and this thing is actually called octahedron. So I'm sorry guys, I just not realized. Anyways, we've now got the regular icosahedron. Yeah, exactly as we were saying before, many polyhedrons have triangles as their faces, and so does the regular icosahedron. It has 20 faces and each face is a triangle. So we've got 20 as the number of faces times the area of each face of each triangle. So yeah, 20 times the formula we found before of a equilateral triangle. Yeah, exactly. See, now we can use it. We don't need to do all the derivations again because we know the equation, we found it. And it has to be an equilateral triangle because, you know, all the edges of a regular polyhedron are equal, because that's what basically a regular polyhedron is. All the edges and all the faces are equal. So yeah, and simplify this, we get 5 times square root of 3 times x squared. Yes, exactly. 5 times square root of 3 times x squared is a formula, the surface area formula of a regular icosahedron. Looks really familiar, right? It's like dice, exactly. The ones we use when we play a board game. So the number of faces, 6. Each face is a square. Area of a square, side times side. We named the side x, so x times x, x squared. So now we've got the formula, the surface area formula, of a cube. 6, the number of faces, times x squared, the area of each face. Here we go. Yo, we've got the regular dodecahedron. Yeah, dodecahedron. Dodeca in Greek means 12, so that's where it got its name from, since it has 12 faces, and each face is a pentagon. And so we have 12 as the number of faces times the area of each face. In our case, it's a pentagon, so we need the area of a pentagon right now. How do we find the area of a pentagon? First of all, we separate it into 5 identical triangles that by linking each vertex to the center. Then we could do 5 times the area of each triangle. In our case, we have x, the side length, as the base of the triangle, and the apothegm, the line from the center at right angle to the side, as the height. So now we need to substitute the apothegm. However, in this case, we cannot use the Pythagoras theory, because this is not an equilateral triangle, so the hypotenuse is unknown because it's not x as in the previous cases of the tetrahedron and octahedron. So we need to use trigonometry, and I will show you how right now. A second before you move on to the trigonometry. So how do I know that this is not an equilateral triangle? Basically, an equilateral triangle has 60 degrees as its interior angles, but in our case we have 54 degrees as the base angle theta. How do I know that? I calculated the interior angle of a pentagon and I got 108. Dividing it by 2, I got 54 degrees. How does that work? So basically, the line from the vertex to the center bisects the interior angle, so the interior angle divided by 2 is angle theta here, and we got 54 degrees. And 54 degrees is not 60 obviously, so it's not an equilateral triangle. The interior angle of a pentagon is 108 degrees. Dividing it by 2, we get 54 degrees, which is angle theta here, as we did before. This is a right angle because the apothegm is basically a line from the center of the pentagon at right angle to the side. That's the definition of apothegm. So this is a right angle and this is a right angle triangle. Since it's a right angle triangle, we could use the tangent. So tan 54 degree is the opposite, the apothem, over x divided by 2. Rearrange the equation, we get the apothem equals x over 2 tan 54 degree. Now we put this into the equation we got earlier, which was 5 over 2 times apothem, which is this, x over 2 tan 54 degree times x. Simplify this, we get 5x squared over 4 times tan 54 degree. And that is the area of a pentagon. Guys, remember, we are trying to find the surface area of a regular dodecahedron. So we put a formula we found for the area of a pentagon back into the equation. So we get 12 times 5 times x squared over 4 times tan 54. Simplify this, we get 15 times x squared times tan 54. And exactly 15 times x squared times tan 54, and that's a surface area formula for a regular dodecahedron. Yeah, if you did it with the top angle over here, the 36 degree angle, you would get 15 over tan 36 x squared at the end. If you want to check out the process, pause the video and check it out. Don't worry about it, but though, it's the same thing. If you put in the calculator 15 over tan 36, you will get the same answer as 15 tan 45. And somehow it's equal to this, as Google says so. So I guess if you don't have a tan function on your calculator, you could use this. And since all these are equal, we've got 3 formula for the surface area of a regular dodecahedron. 15 over tan 36 times x squared, 15 times x squared times tan 54, and 3 times square root of 25 times 10 times square root of 5 times x squared. Guys, as a summary, we've done the tetrahedron, the octahedron, the icosahedron, the cube, and the dodecahedron. And once we have a regular polyhedron with triangular faces, we use this formula: the number of faces of the specific polyhedron times square root of 3 times x squared over 4. And for the tetrahedron, we've got square root of 3 times x squared. For the octahedron, we've got 2 times square root of 3 times x squared. And for the icosahedron, we've got 5 times square root of 3, square root of 3 and times x squared. And for the cube, we've got 6 times x squared. For the dodecahedron, we've actually got 3 of them. 15 times x squared times tan 54, or 15 over tan 36 times x squared, or 3 times square root of 25 plus 10 times square root of 5 times x squared. That's all for today. I wish you enjoyed the video, and don't forget to subscribe. Well, it's my first time making a video. I'm sorry I was starting a bit, but I wish you could understand that. Anyway, see you next time.